Bismillah ar-Rahman ar-Rahim. Today video about Snubber circuit, RC circuit. Okay. Before we start, we have here single line diagram for simple power system, just source and cables and transformer. Okay, we start with source. We have source here 33 kilowatt and 50 hertz, and the positive sequence impedance 1 ohm. That mean short circuit level about 1000 MVA, and our zero sequence impedance is different from positive sequence impedance. Okay, this about source. Then we have here circuit breaker BRK1 with logic, time logic for operation of the circuit breaker, when the circuit breaker open or close, in which time in the simulation period. Then we have cable. Here we model the medium voltage cable just by stray capacitance, and the transformer is 300 kVA or 0.3 MVA, 50 Hz, primary connected in delta, secondary in star, AC star. And here we have impedance Z of transformer is 4%, that means 0.04 per unit. And also we have no load losses and copper losses. Here is about 0.2, no load losses 0.2% of transformer rating, and full load losses is about 2% of transformer rating. Winding voltage primary 33 kilovolt, secondary is low voltage 400 volt. What else? It's saturation window. Here in this we activate or enable saturation enable, and in saturation window for transformer, this I get this default data for transformer. Important data is knee point voltage, that means at this voltage 1.17 per unit the transformer get saturated according to its magnetic core, transformer core construction and area. And magnetizing current is about 1.6% of rated current, and rush decay time 1 second. It should be less than 1 second. This is the important data in saturation window. This for transformer. I have here load 0.03 megawatt controlled by this breaker BRK2. Here this branch, what we call it, Snubber circuit or RC circuit, resistance with capacitor in series. Also we control this branch by this breaker. Alright. Okay, what I want to do here is I want to know when this transformer de-energized by upstream circuit breaker, when the transformer at no load, the relation between reactance of transformer XL and stray capacitance of cables, because here when this breaker de-energize transformer with cable, the stray capacitance charge, I think there is oscillation between transformer and stray capacitance, and this oscillation may be get dangerous, or may we get high risk if this stray capacitance and transformer leakage impedance get in resonance. May we get high transient over voltage or high over voltage for the transformer or cable itself. Okay, let us start the simulation with capacity. Here by this slider I can control the capacitance of stray capacitance. Alright, medium voltage cable here, the size of medium voltage here is 185 mm square. According to manufacturer, the stray capacitance of these cables about 0.2 microfarad per kilometer, per 1 kilometer. At the beginning I will start simulation without any stray capacitance, 0. We run simulation. I forget things, the breaker here closing for 1 second. After 1 second the breaker opening, de-energized transformer. Okay, at 1 second. No, I think here, no, this circuit breaker open, close for 1 second, close for 1 second. So why we circuit breaker close for 1 second, after that the circuit breaker open. Let us check runtime about 3 seconds, it's okay. And at this time the low voltage circuit breaker open for 10 seconds, more than runtime. And the breaker of Snubber circuit, the logic BRKC, where is BRKC? Here. Okay, this breaker or this one. So Snubber circuit is open also for more than runtime. And here I have airs fault, but at this time also off. Okay, save, run. Okay, if we change open 1 second, then close. Okay, the circuit breaker close for 1 second, then I think the simulation I must use here a little stray capacitance to do this simulation. Yes, and our circuit breaker close for 1 second, then open. Yes, close for 1 second. Here you can see the voltage. Close for 1 second, then the circuit breaker open. Also, I have voltage across circuit breaker contact, VCB. You can see here VCB. When the circuit breaker closed, the voltage across circuit breaker contact is 0, but when circuit breaker open, we get the system voltage, nominal voltage to earth. The measurement of voltage here to earth, not line to line. Okay, let us examine the effect of stray capacitance or system capacitance. So we increase the capacitance. Let us say our cable is 1 kilometer. That means 0.2 microfarad the capacitance. Run simulation. Okay, one with the voltage V2 here at transformer terminal. I think there is no any over voltage for transformer, but the TRV across, we get transit recovery voltage across circuit breaker now is coming little bit high than before. Okay, let us say we have 2 kilometers. That means the stray capacitance is 0.4. Here the risk, this transformer, when the circuit breaker de-energizes, there is transit over voltage across transformer terminal and across circuit breaker contact. That means the transit recovery voltage. So that means we should not de-energize unloaded transformer with long cable, because there is, when the transformer de-energizes, there is energy trap from stray capacitance with transformer. That means there is oscillation, but I think this oscillation damping very quickly, especially if we have resistance. As we know, the resistance damp the oscillation. The resistance is damping the oscillation, especially if this transformer have more no load losses. The damping is get away, or very fast damping for this oscillation. So the solution here, we can use this Snubber circuit to prevent transformer and cable from overvoltage when de-energize unloaded transformer with long cable. But before we simulate RC Snubber circuit, let us check with load, when the transformer loaded or just close this breaker, just about 30 kilowatt. That means 10% of transformer rating. Run simulation and we check. Here no over voltage and also across the circuit breaker, because for circuit breaker there is a danger of restrike. When the TRV is very high, that means the recovery voltage is more than insulation. Maybe there is a risk of restrike across the circuit breaker contact. Okay, with load there is no problem, or there is no risk for de-energized transformer with long cable when transformer loaded or just loaded by 10% of its rating. But let us remove secondary load. Check. Yeah, when the transformer are loaded, we have transient overvoltage. So according to Snubber circuit manufacturer, the capacitance is 0.2 microfarad, and the resistance is about 30 ohm. According to manufacturers like Strike company, this is a manufacturer standard. We check by this value. I think there is no any over voltage for transformer, but still TRV there is a risk of high TRV, transit recovery voltage. Okay, this for de-energizing of transformer and how we use RC Snubber circuit as the transformer terminals. I think here Snubber circuit is better than serial resistor. This RC circuit it works like to avoid this over voltage just by the Snubber circuit draw when we get over voltage, the Snubber circuit conduct or draw more current, and then we prevent transformer from over voltage. The principles is look like serial resistor, but maybe serial resistor not work for this over voltage. The RC circuit I think is good solution here, and it's very important amazing circuit to prevent transformer from any over voltage due to oscillation with stray capacitance or whatever over voltage. All right, this is for Snubber circuit. Okay, let us remove off Snubber circuit, and I want simulate another thing. That means when there is earth fault upstream in the upstream bus bar or on another feeder. So let us say there is earth fault at 1 second and duration of fault is 0.5 second, and let us our circuit breaker is closely along run time, and we see if there is any effect of this earth fault or as you see here, because our system is solidly air sealed, so there is voltage dip at phase A, because here our earth fault from phase A to ground, so we get there is no, but I think Snubber circuit no Snubber circuit is on, so close, so off, run again. Let us see, the fault resistance is very low and the earth fault is very high, and we have 2 kilometer cable here. There is no problem for voltage when the earth fault cleared at 1.5 second. There is no problem. Alright, so we can check this video for showing the importance of snubber circuit. Okay, that is all for today video. See you next video. Thank you for watching and subscribing and supporting us.